Hello and welcome everyone. My name is Lauren Dow. I'm the Communications Coordinator, and welcome to today's Research Off hosted by the National Road Research Alliance, or NRRA. My Word document is not working where I have all of my introductory content, so I'm going to do the best I can to introduce our presenters today, Drs. Boris Seaton and Raul Velasquez, and they are both deeply involved with uh, our geotechnical team of the NRRA and are involved in quite a number of projects. uh, but they are both, um, again, deeply involved in the geotechnical industry and research. And so I will go ahead and let them begin talking about their Recycled Bases project.
Thank you, Laura. Good morning, everyone. Thank you for spending part of your morning attending this Research Pays Off. I'm going to be co-presenting with Professor Boris Seaton from Michigan State University. And I'm excited to be providing some updates and some summary of results of this interesting NRA research project on recycled bases. Bora, do you have, would you like to say anything before we start?
I think we're good to go, Raul. You go ahead and we'll switch back and forth.
Okay. So as I mentioned, what we're presenting today is a part of an NRRA geotechnical research project entitled Determining Pavement Design Criteria for Recycled Aggregate Base and Large Stone Subbase. This is a major effort that started in 2017. So here today we're gonna be presenting part of the results and summary. We're not gonna be including the nice work done on the large stone subbase. If you're interested about more information related to this project, please visit the link below where we have all the reports, presentations, and details of the project. The research team leading this effort comprise researchers and faculty members from Michigan State University, University of Wisconsin-Madison, and Iowa State University. The TAP, who reviews all the work, is quite robust and comprehensive. We have DOT members from different states. Half of the project was led by, in terms of TL, the technical liaison was led by John Siegmeyer. Then I finished it the second half. But before we start, I would like to just give you a brief overview of what we do, the cool things that we do, and who we are in terms of the geotechnical team. So the NRA Geotech team is comprised of technical experts in the area of unbound and bound materials that are found on their pavement surfaces. The chair of this committee is Terry Baudry from MnDOT. So we have, the team is comprised of agency, associate, and friends and support members. Agency members are staff from different DOTs. We have about 8 DOTs, including a recently added staff from Illinois Tollway. Associate members, we're very happy to have because we have covered a comprehensive set of experience. We have members from industry, technology developers, academia, and contractors. A quite wide range of members that provide excellent input in our efforts. And then we have friends and supporting staff. So if you're interested in the things that we do in the Geotech team, please join us in our team meetings. We meet every first Thursday of every month from 12:30 to 1:30 p.m. The link where you can access the information for accessing the team meetings is in that link below in this slide. So please join us if you're interested in what we do in the Geotech team. Before we start, I just want to show you, highlight what the cool things that we do and what make us different. Is that we have a set of we leverage the experience for all these members. So we solve practical problems related to pavement foundation, yet we use fundamentals of soil mechanics, both saturated and unsaturated soil mechanics, the expertise from years of experience in instrumentation, accelerated road facilities, pavement facility testing facilities, advanced NDT testing, and computational methods. So what is unique is that we have these members that bring their own skills to solve these complex research projects. And one of the plus too is that we work closely with Minroad operations and Minroad staff. We are very nice and providing us all the data and information. And again, you guys, most of you that are attending today's seminar understand that this is a one-of-a-kind facility that allow us to test technology methods related to payment. So that's also unique for our team. So what is the motivation for this study? The motivation of the study was mainly to improve and refine design guidelines, specifications related to recycled concrete aggregate and recycled asphalt pavements. So refining the specifications related to recycled aggregate bases. And to test and monitor the performance of recycled aggregate bases under a unique environmental conditions at Minroad. And when we say unique environmental conditions, we mean that these materials are subjected, as we, you know, if you live in this region, to extreme fluctuations of temperature that can provide a significant information in terms of performance. It's also is subjected to not just big changes in temperature, but also freeze-thaw cycles. And also very importantly, we have in this facility, we have very shallow water table, which create this complex moisture distribution inside your pavement foundation. So that's kind of unique set of situation for studying materials such as these recycled bases. So the research team did a significant literature review and found that there was limited information about field performance of these materials. There was limited information about how to properly mix recycled concrete aggregate and RAP. And that was also an additional motivation to perform this study. As I mentioned, there was inconsistent design methods and construction specifications related to recycled aggregate bases. And there was a lack of information available for design inputs. And another important outcome from this work is the prediction of mechanistic based parameters for design purposes based on simple experiments. And Bora is going to talk a little bit more about that, how to predict stiffness based on simple testing. And that's one of the outcomes from here, from this project. So what are the Minroad recycled aggregate based cells? So our cells 185, 186, 188, and 189. The cells are located in the low volume road loop on the west side. 185, 186 are founded on sand subgrade. And 188 and 189 are founded on clay loam subgrade. So keep that in mind. In terms of thicknesses, they're all the same. The top material is the same. It's a 3.5-inch super paste mix design, 12.5 maximum aggregate size mix. So 185, 186 are the recycled concrete aggregate bases. One is coarse material, 186 is finer. And then 188 is the control section where we have limestone aggregate. And then 189 is a mix of recycled concrete aggregate and RAP. We can talk a little bit more about the performance and the approximate ratio of these two materials later on in the presentation. Bora.
Thank you, Raul. So thank you again, everybody, for being here. So these are the 9 different materials that we tested for the recycled base test sections at Minroad that Raul just mentioned. Again, we had a sand subgrade on underneath coarse RCA and fine RCA test sections, and clay subgrade, clay loam on the RCA RAP mixture base and the limestone base. And we have a select Groner Barrow material here on the top or at the right above the sand subgrade and clay subgrades. And here are some pictures of the coarse RCA, fine RCA, RCA RAP mixtures and limestone. One thing that we also wanted to touch bases with the class 6 aggregates and class 5Q aggregates that are used as a base on top of the another large stone subbase sections that we are not going to cover here, but we would like to discuss those materials characteristics in this and how in this presentation and how their performance is compared to recycled bases. And here is the limestone, as you can see, is a very like a fresh crushed aggregate from the quarry. Class 6 aggregates and Class 5Q aggregates, they are basically a mix of RCA and REP materials, as well as you can see from the figure on the left, bottom left, the Class 6 aggregate. It is very dark, and you can see even the black dot particles there. There are basically REP materials. And Class 6 aggregate had actually even have more REP material than RCA REP mixtures based on one of the REP binder content measurements. And on the other hand, Class 5Q aggregate at the bottom on the picture, you can see it is very whitish, similar to coarse RCA and fine RCA, and it didn't have much of a REP material. And then even the smell of the Class 5Q aggregates very intense, the cement smell that you could have taken when you open the buckets that we store these materials. So basically all these materials except limestone and of course the subbase and subgrade layers were recycled basis materials. That's why we compare these materials characteristics. Yeah, next slide, Rob. And here are the specific analysis that we conducted. We had a very comprehensive laboratory testing, but we won't be able to cover all these. But these are the list of index properties. These are very important, and as Raul mentioned, we try to use these index properties to predict to develop correlation equations, relationship equations to predict the resilient modulus, or shear strength of the materials by using some of these simple index properties. So agencies or contractors or industry personnel didn't have to run resilient modulus test to use as an input in the payment ME analysis. And then saturated and unsaturated properties become very crucial. We wanted to know how the permeability of recycled bases compared to limestone is. And then we did very unique study that not many people did to try to understand the unsaturated conditions, unsaturated soil conditions, how do they impact the performance of these materials. And we tried to get the angularity measurements of these materials if they change within the materials with the stereophotography, and also try to determine the particle size distribution and the shape characteristics of these materials. We won't talk much in this presentation, but I can tell you that the angularity of all materials were very similar to each other. And then one of the main things is the gyratory compaction and abrasion test, which is very crucial, and we have the data show, even though we had the original gradation of the coarse RCA was very coarse material that you will see in the next slide. After compaction, that gradation changes, so you may not want to apply the 100% or 95% compaction degree on some of the coarse RCAs because it may cause a significant gradation change. And if you come to the next slide, please, Raul. Here is the particle size distribution of the materials that we will discuss today. As you can see, the bottom two line, the coarse RCA and Class 5 aggregate seems in the beginning have a coarser gradation compared to other four materials, but again, after compaction, their gradation also shifted to the right to become finer, close to the other gradation characteristics of the other four materials. Next slide, please. And overall, what we learned from laboratory testing, all our materials based on the AASHTO soil classification system, A1A materials which are good quality and appropriate materials to be used as a base materials. All of them were non-plastic. But one important characteristic is the absorption is expected because of the leftover cement content. RCA materials, recycled concrete aggregate materials had higher absorption, and this is related to the mortar content, as we put in the second line item there. Higher the mortar content, higher absorption value your RCA will have. This is good up to having a good absorption may have some advantages that it absorbs water and which starts rehydration of some of these unhydrated cements or rehydration of some of the remaining cements in the RCA materials, recycled aggregate materials, and increase some stiffness or yield in higher stiffness values. However, if too much absorption may keep too much moisture in it, and eventually in the long term may cause some performance issues. So it needs to be balanced properly. And as you can see in the absorption, fine RCA had the highest absorption when, of course, limestone had the lowest absorption value. And with the asphalt binder content, we will, in our final summary slides, we will talk more about the results, but there are chemical extraction method and ignition method. I mean, both methods, extraction method provides a little bit more reliable results, but it's not as fast as the ignition method. So it may be recommended the ignition method to use if time is a constraint. Next slide, please. So again, like I discussed with the pictures, the slides that we have the pictures of these materials, class 6 and class 5 aggregates, basically recycled base aggregates 2, and class 6 aggregate were more similar to the RCA REP. It had a high REP content, binder content. Class 5 aggregate were very similar to coarse RCA in terms of gradation and in terms of mortar content. When we come look at the hydraulic conductivity of these RCAs, there is sometimes concern about their permeability, but both in the field measurements and in the laboratory measurements, hydraulic conductivity, KSAT, of these materials were higher than limestone. And we will get to this a little bit, but fine RCA had a higher porosity than the coarse RCA, and we kind of speculated, we kind of thought that the porosity, of course, has a direct influence on the hydraulic conductivity, and as expected, and how the materials that has higher porosity will end up having higher hydraulic conductivity. One thing that we may say with the abrasion values, RCA seem to have higher abrasion, and I mean, the limestone has better abrasion resistance, and which is expected because we will get to that some of the RCA materials, some of the mortar materials look like aggregate size shaped materials, but they are not actually aggregates. They are just clumps of cement particles combined with finer aggregates and finer sand materials and turn into aggregates, coarse gravel size aggregate sizes. And when you apply the abrasion, either through gyratory compaction or through the LA abrasion, those mortars are broken. And that's why this study found that materials, aggregates with our recycled concrete has a little bit higher abrasion compared to limestone. And then we look at the relative breakage under compaction. As I mentioned before, especially coarser graded RCAs may have a high relative breakage, and that is directly related to the residual mortar content. And if you have high residual mortar content on your RCA material, you tend to have high breakage potential, which will make your, under the compaction, it will alter your original gradation and end up having a lower, finer gradation curve, which may impact the characteristics, stiffness, and the permeability of the material a little bit. And again, if you have the angularity of the material impacts the breakage. If you have more rounded aggregates, of course, the breakage ratio will decrease significantly. Next slide, please. And one thing with especially when we were running the hydraulic conductivity test with the fine RCA, we realize RCA materials attract more water, and that means it's directly related to the water absorption. So they absorb high water, and if you have higher mortar content, that will have higher absorption. And one thing that we saw with the water repellent studies, RCA materials have very high hydrophilicity, so they like water, they absorb the water. On the other hand, mixing it, the REP RCA mixtures or class 6 and class 5 aggregates had much lower hydrophilicity. Even some particles were hydrophobic because of the binder content that you have it. So if permeability becomes a concern, it is a really good idea to mix the RCAs with REP in the long-term performances. And cementation, again, the picture here, basically water is being sucked in, and some of the cement particles are rehydrated, and even unhydrated cement left there starts being cemented and may cause some, it reduces some permeability of the material. Next slide, please. And another thing with the needs to be careful. While in the field, we saw that RCA and coarse RCA materials or other recycled-based materials still perform better in the 2-3 years of performance than the limestone material. We will get to that. Raul will start that soon. But one thing, after 5 freestone cycles, when we were determining the mortar content of the RCA materials, as you can see, these large size particle that's supposed to be aggregate had a huge mortar attached to its surface, and once it's exposed to the 5 freezing and thawing cycles, it causes a huge crack, and indicating that the RCAs will disintegrate when they are exposed to freeze and thaw cycles. And how much this will impact in the long run is one of the questions that in the short term, in the 2-3 years of term, it didn't impact the stiffness significantly, but we may want to see such effect in the long term, but we don't know it yet. But after freeze thaw cycles disintegrate, it is very clear that the mortar is being disintegrated. All right, Raul.
So now let's switch gears a little bit. Let's move into, as Bora mentioned, into the field performance at Mineroad. So before during construction, we perform extensive testing of these recycled aggregate base cells, which included in situ density and moisture content measurements using traditional methods like the nuclear gauge, spot testing, sample collection. We also did DCP testing for shear and stiffness estimation, shear strength, lightweight diffractometer testing, intelligent compaction by Ingius, David White, falling weight diffractometer tests as well. So here I'm going to show some of the results that we got from during construction. Here we're showing the LWD stiffness for those 4 recycled aggregate base cells. Overall, stiffness are very similar for all the 4 bases. It varies between 10 to 15 KSA. In general, the coarse and the fine RCA shows slightly higher stiffness than the limestone and the mix of RCA and RAP, with the one with RAP being showing the lowest. And there could be many reasons why we see this we see this trend, and we will discuss that later on during this presentation. For FWD, the trends were very similar. Again, the RCA bases were showing higher stiffness than the ones with the limestone and the RAP material. In terms of performance monitoring, we continually measure soil temperature and moisture. And from those measurements, those profiles, the team estimated frost penetration depths, freeze-thaw periods, and freeze-thaw cycles to determine the performance of these materials under extreme environmental conditions. Mineroad operations also did very nice work helping us out with FWD testing, frost heave and thaw settlements, very accurate measurements actually, rotting, roughness, and other pavement distresses. This is how the typical instrumentation for these recycled aggregate base cells look like. Kudos to Len and all the people at Mineroad for doing an outstanding job instrumenting these cells. Typically, we have, for this experiment, we have 12 thermocouples across the pavement foundation, and then 4 moisture sensors, including sensors in the base, in the subbase, and in the subgrade. Just to know that for the people that are not familiar with Mineroad, we have an outside lane where we call it the environmental lane, where we study the environmental effects, where we have the instrumentation, occasional traffic, and then the main traffic is the inside lane, just FYI. We also collected weather information for our analysis, air temperature, precipitation, solar radiation, and wind speed in a nearby station. So I'm going to show you some early pavement distress data. As Bora mentioned, we collected about 2 to 3 years of performance of these cells. In terms of rotting, in general, all the cells are performing well. Very little distress. In terms of rotting, we have less than 0.2 inches. Very little difference between them. Perhaps RCA cells show a slightly lower rotting. In terms of roughness, they're all below the limit, target limit for the roughness, and they're pretty similar. Longitudinal cracking, it was not observed for the first 2 years. Here's some nice survey from Mike and people at Mineral. Thank you for doing all this work. And an interesting observation we got is in terms of transverse cracking. So early on, after 2 years of material being in there, we have some transverse cracking observed in cell 189, which is the one with a mix of RCA and RAP. No transverse crack measure for the other cells. Looking back at the intelligent compaction quality data collected from David White and Ingius during construction on both the subgrade and the base material, we observed that the cells that have more uniformity and less spatial variability were the ones that are currently not, we don't observe transverse cracking. So here I'm showing you the mapping of a resilient modulus for cells 185 and 186. And you see that most of the colors are purple, dark, well, I don't know, that's brown, I think, and dark blue. You don't see a lot of significant variation. Now, if I go into what was measured in the foundation, in the subgrade for cells 188 and 189, then you see a lot of more red spots, meaning weak spots, resilient modulus less than 8 KSA for the subgrade, and also a lot more variation, a lot more of color, so more red, orange, yellow, green, a lot of more spread, spatially spread on the subgrade for 189. So that's interesting to observe because we know that thermocracking is mostly driven by binder type, performance grade, aggregate type, mixed design, and there is some effects, but not significant effects from the foundation. So this is a quite interesting observations we have, and we have collected intelligent compaction data in other parts on our cells in Mineral that we observe similar trends. So we're going to keep an eye on this interesting result.
Thank you, Raul. And we will talk about a little bit of the what type of data that we collected within the base layers in terms of volumetric water content and thermocouples. Here is one of the slides that shows how the volumetric water content changes in 5-inch, 14-inch, 17-inch, and 20.5 inches depth from the ground surface. In the test section that we have 12-inch thick RCA RAP mixtures. And as you can see, at each depth we kind of see how the volumetric water content changes over time. And the one in the deepest had the higher water content, which is attributed to the long, higher groundwater table level. And one thing that we wanted to point out here, how the volumetric water content sensors work is like it is basically soil. It's basically measuring the dielectric constant of soil, and when the soil is fully saturated or close to fully saturated with the water, it starts picking up these volumetric water content measurements. And if there you see we label it as a freezing, where you see a steep decline on the curve, that shows that the soil starts something happening to the water content. And if you look at the time interval there, in the January it started, actually even before January and December, that means the weather is getting colder, soil starts getting below freezing temperature, and of course volumetric water content measurements decreases significantly, and that means ice starts forming. And then it stays stable, frozen for a while during that period, that give us the frozen time of that particular depth in that particular test section. And then when you come to the March, as you can see, we see that steep increase in the volumetric water content, indicating that formed ice starts melting and then being fluctuating or stabilized over the period of time. And why we show this graph, we basically and this is the first thing, like we will show the thermocouple readings. Thermocouples, we assume sometimes where we use this volumetric water content to confirm that soil is really frozen when it is below 0 degree of Celsius, because you see a sudden decrease in the water content measurements, indicating that yes, water is also start freezing. And we use this volumetric water contents and thermocouple measurements I'll show you in a bit to determine how long of a period the soil is stayed frozen, and how long does it take for entire depth to thaw. And here is the readings, the soil temperature readings at different depths that Raul mentioned, from all the way to the 3-inch depth to 72 inches depth in each test section. And this is for the temperature variations for test section built with 12-inch thick limestone. And as you can see, it fluctuates a lot, and it is below 0 degrees Celsius or 39 degrees Celsius below the freezing line, and it stays frozen during that period of time, then it thaws. Next slide, Ro. And here we draw these isotherms. Again, we assume the 0 degrees Celsius. Anything when the soil temperature goes below the 0 degree of Celsius, we start assuming that it starts freezing. And it, as you can see here, the freezing time can be determined. And then the red line, the black points are showing the freezing front, that how it changes with depth. And then the red lines are showing when the thawing starts and at what depth it starts. Again, it starts freezing in the top, and it takes some time for freezing front to reach to the bottom of the test sections. And then it starts melting again, thawing again at the beginning, and it takes some time for that thawing process to be completed all the way to the bottom of the test sections. And as you can see, in the first year in 2018, when frost depth was below 5 feet, it was almost 6 feet in the next year. So it had a little bit colder winter in 2019. Next slide, please, Rob. And here again, ISO 0 degree Celsius isotherms, and again, this here we kind of determine what is the maximum frost penetration depths and what is the freezing period for each materials and thawing period for each materials, and determine which material that it takes longer time to freeze and for which material it takes longer time to thaw, which is very important. And we kind of summarize these for each year in the for each recycled base layers here. And as you can see, the thawing periods were higher for RCA, so it takes a little bit more time for RCA materials to thaw completely. And this is kind of related to two things. Of course, the first thing is thermal conductivity. We hope that in the future studies this will be measured for these materials. But what the current data that shows us, absorption data is very important. And the higher the absorption of your material, it will absorb more water, and it will keep more water, which will turn into more ice, forming more ice. And of course, that higher rate of ice content will take more time to thaw. That's why we see higher thawing periods for RCAs compared to 12-inch thick limestone materials. Next slide, please, Ro. And one thing that we see higher frost penetration depths for limestone, and this can be attributed to, again, the absorption and thermal conductivity, because lower the absorption, that means low amount of water is being held on to limestone. It has very low absorption value, so it allows water to penetrate much easily and start freezing at the bottom of at higher depths. And while if you compare the frost penetration depths, they are not that significantly, 20, 30 centimeter, depending on the materials that you're looking into. But still, I think thermal conductivity is a key point, and the absorption characteristics of these materials basically have an impact on these frost penetration depth. And then we also look into the 2 years of performance, actually 2.5 years of performance of these recycled base materials. On the first column, we have the coarse RCA base, and second column are fine RCA base, and third column crushed limestone base, and the last column is RCA rep base. And as you can see, in the beginning, even before the first freezing period, fine RCA and coarse RCA base layers have much higher stiffness from the elastic modulus that were collected from the FWD test before the first freezing period. And RCA rep had higher stiffness than the limestone materials itself too. And when we look at how they perform during the freezing and thawing cycle, so both in the first thawing and second thawing periods, again, coarse RCA and fine RCA materials overperform the limestone and RCA rep. And if you compare the RCA rep, after first 2 freeze thaw cycles, first cycle and the second thawing period, RCA rep also provide superior performance in terms of elastic modulus to crushed limestone base. And one thing that I wanted to focus here, when you look at the coarse RCA and fine RCA, after the first freeze thaw cycle, you don't see much change in the stiffness, even have little increase in the stiffness for the fine RCA. And in the second thawing period, the performance starts decreasing a little bit, but that decrease rate is not as significant that we see in the crushed limestone elastic modulus. So this graph here shows that coarse RCA materials, recycled base materials, provide higher elastic modulus performance than the crushed limestone. And on top of that, they have better freezing and thawing durability for the first 2.5 years of data that we get. Next slide, please, Raul. And what did we learn from field performance? I think the sensor installation and prediction of frost depth, penetration depths, and freeze thaw periods were very successful. And based on the construction data, LWD, lightweight deflectometer, elastic modulus data, and intelligent compaction data, and that we saw that also FWD data that we didn't mention here, but fine RCA are right after construction and also through the right after construction had high stiffness values, elastic modulus and resonant modulus values. And coarse RCA was the second performer. Limestone and RCA rep, they are kind of very similar to each other. And DCP shear strength values were a little bit lower for RCA bases, but it is really very tiny bit point that we take with the DCP. So the data that we collect from the LWD, intelligent compaction, and FWD seem to be a little bit it would be more reliable. Then we look at the overall field performance of this data. On the other hand, in the 2.5 years of data that we collected, fine RCA and coarse RCA really overperform, like provided better stiffness and performance compared to limestone aggregates, and RCA rep were provided a little bit lower performance than the fine and coarse RCA, but had higher performance on limestone throughout that 2.5 years of monitoring. So material selection that Raul mentioned, of course, not everybody will have a chance, or there may be time constraints to do all these tests on each test section. So especially during the design stage, how we can predict, how we can select the appropriate materials. So we kind of come out with assessing specific gravity, GS value, absorption and residual mortar contents of RCAs might be very important information, and looking into the water absorption characteristics. So maybe put some limits on the absorption characteristics. Based on this study, we kind of suggest, not hard line, but absorption value may be limited to 7%, so you don't want to go above 7% of absorption for the pure RCAs, and mixing RCA rep will decrease that absorption value. But again, based on this study, the data that we collected, we may suggest that keep that absorption value below 4.3%. And for the hydrophobicity, again, to be on the conservative side, you may want to use the Ignatian method, and which is a little bit faster to determine the asphalt binder contents too. And one thing that we overly realize that since you're by adding REP, you're increasing the hydrophobicity, so aggregate material became water repellent, doesn't want to suck water in much. That would impact the freezing, improve the freeze-thaw durability a little bit more. And if you add more REP in the mixtures, the hydrophobicity of the material, if you add the hydrophobicity of the material will increase, and the drainage will not increase much. And again, one thing with the RCA materials is the calcite precipitation issue that we may that may cause some drainage issues, and which I will talk in the next few slides. Next slide, please, Ron. And again, abrasion, RCAs seem to have a higher abrasion, so it's recommended that gradation after compaction needs to be looked at. And for coarser RCA, maybe use a little bit lower degree of compaction. And the permeability-wise, overall, at the moment, the field and the laboratory permeability test results show that hydraulic conductivity of RCA seem to be higher than limestone. But of course, long-term performance needs to be checked in the future studies. Next slide. And then we also look into the, okay, we have all this field and laboratory data, and wanted to do some recycled aggregate base layer design, run some pavement ME simulations, pavement mechanical empirical design simulations to check to see if we use lower RCA materials or RCA REP mixtures at a lower thickness, would we get the same amount of performance that we would get with the 12-inch thick limestone base? And the results were yes. I mean, there are some simulations that we run. You can get the stiffness performance of the material, the overall pavement performance prediction, by using 4-inch of some of these materials instead of using 12-inch limestone base. Of course, 4-inch may, I mean, this is just a simulation, so this needs to be verified in the field study, but based on this pavement ME analysis, you can decrease the thickness of the base layer if you use REP material significantly compared to using freshly crushed quarry aggregate base materials. One thing that needs to be picked on, again, the high absorption values of RCA needs to be checked and limited. And you may want to have highly permeable sub-base if in some of the cases with these RCAs, and maybe use some specific geosynthetics. Again, calcite precipitation may be an issue, so you may want to use some geocomposite design between the sub-base and base layer to minimize that calcite precipitation issue. And again, we talk about the gradation, especially for coarser RCA materials. Gradation after compaction needs to be checked. And one thing that our study find, you don't need you need a, for instance, resonance input or permeability input that you need to put in your pavement ME design. But we developed some equations and correlations that some majority of these input parameters can be estimated by just measuring the specific gravity and absorption values of these materials. Next slide, please, Rob. So what are the environmental aspects of recycled aggregate bases? It wasn't part of this study, but we wanted to touch bases with this. We have quite a bit of experience with this and wanted to summarize the last 10 years of studies that we've done on this topic. So leachate of pH of the REP layer changes from pH of 11 to 12. And some of our studies show that addition of REP may reduce this pH slightly, but not significant, or mixing REP, this RCA, with the regular aggregates, conventional aggregates, decreases that value a little bit, but not significantly. And carbonation, what we did, we exposed these RCAs to the carbonation, and that kind of tend to decrease the hydraulic pH of these materials significantly, almost 2 to 3 magnitudes. And this happens in the field too. When you put the REP layer there, over time it will carbonate it and the pH of the REP material itself will decrease. But the main thing, and this is no concern at all, you have a sub-base or some sort of subgrade under REP layer. And whatever leach from the base layer that goes to the sub-base or base layer, and our research studies show that once that leachate come from recycled aggregate base layer reached and leached through the sub-base or base layer, your effluent pH beneath of that sub-base or subgrade 7.5 to 8.5, even lower than that. So in terms of environmental concerns, in terms of high pH, is not really a concern, because REP sub-base and subgrade layers underneath REP layer kind of disperse and dissipate that high pH value within itself. And then in terms of leaching of metals, we've done many laboratory and field leaching test studies on this, and also did geochemical modeling analysis. Our results show that, including the numerical models that we did, groundwater contamination numerical models, none of the metals exceed the pH limits at natural pH of REP, so at their pH of 11 and 12. And the only time that we see this can happen if you pour some sort of acid poured on this REP, like very harsh, highly concentrated acid, which is very unlikely in payment systems. And that REP pH, not the sub-base or clay pH, REP pH goes below 6, then yes, you start seeing significant amount of metal concentrations increasing, but it is very unlikely that this scenario will happen. There is no acid rain that will decrease the that will leach through concrete or asphalt surface to the base layer and cause significant pH drop in the base layers. And to minimize the metal concentration, large-sized particle RCAs can be used. Our studies showed, multiple studies showed, an increase in, if you use coarser materials, they tend to leach less because of the lower surface area of these materials. And our numerical models show that it takes 4 to 6 years for these elements, contaminants, I mean, not contaminants, but these metals to leach even to shallow groundwater. And when it reached, it's already dispersed. It's already, if it leached 10 milligram per liter, I'm just making it a number. Let's say iron leached 10 milligram per liter. By the time it reached the groundwater, it turned out to be 0.001 milligram per liter. So it dissipates over time. And one main concern, however, with the environmental aspects of these REPs that needs to be answered, we touch bases with this, we're trying to solve this problem some more. Tufa formation, calcite formation, in the long, I mean, it has cons and it has advantages and disadvantages. Calcite formation would increase the stiffness, which will be helpful in freeze-thaw cycle durability. However, it will decrease the porosity and reduce the permeability. And if you use geosynthetics, and if you didn't use the right geosynthetics, it may cause some clogging potentials. So those are some of the environmental aspects of these use of these REP materials in payment systems. Raul, I leave the next slide to you.
Thank you, Bora. So before we open the floor for questions and discussion, we just want to highlight what is ahead and the opportunities that we have for conducting additional research on recycled aggregate bases at Minroad. So we would like to continue performance monitoring. Right now we have about 2 years of performance data analyzed. We would like to add a couple of more years, up to 5 years of information to keep track of the performance of these cells. Do detailed forensic analysis to answer some of the issues that Bora has pointed out during the presentation. Specifically, we would like to assess the changes in index, physicochemical, and engineered properties of these recycled materials over time, placing an emphasis on the recycled concrete aggregates. Bora just mentioned the issue of tufa, the tufa formation. What are the implications of this tufa formation in terms of drainage and stiffness? And get that the data from actually the Minroad cells will be very valuable. And also addressing the issue of the optimum blend between RAP and RCA. Bora talked about the properties of each one, that we can get the best out of each material to have what we call balanced performance mix, which is a mix that has an optimum drainage, stiffness, and strength. Bora, would you like to add any other item on these opportunities before we open the floor for questions?
No, I think this covers it pretty well. What like thermal conductivity, something needs to measure to kind of get a full understanding of freeze-thaw behavior of these materials. I think would be something to study in here too. So.
Thank you, Bora. So with that being said, thank you for attending the research face-off, and Bora and I will be more than happy to answer any questions if they are.
I think they wrote the questions, Raul. So should we go from the top to the bottom, or how would you like to proceed?
Yeah, sure. I have not seen any of that. I was driving the slides, so I don't see any.
So
yeah, I'm happy to read out the questions if you'd like me to.
Sure.
Yeah, that'll be nice.
Okay. So the first question was early on in the presentation, please describe the composition of RCA, and I'm not sure if you ended up going through that or not.
Yes, so Raul, maybe we can show that table that we had at the additional material slides. Do you think?
Yep.
So
Sure.
if you mean how much RCA we had in these materials, it was very challenging. We couldn't really get that, but coarse RCA, fine RCA, and class 5Q were predominantly RCA materials, like 80–70% that we could guess. And the RCA rep and class 6 aggregates were predominantly rep materials. I hope that answered the questions. And this is the typical, more detailed definition and the characteristics of this table shows characteristics of the RCA materials.
Okay. And the next question is, have you noticed white chalky discharge when RCA as base materials during any part of the research?
It was diluted during hydraulic conductivity test. We see this a little bit, but not at high concentrations. It's not like, it doesn't look pure white. It has some white chalky, like white dust size, where it's fine particles that sometimes come out, but not at high concentrations. So tubing was not clogged. We used the same tubing when we were running the hydraulic conductivity test, and it wasn't pure, but we sometimes see some of the fine particles.
And related to slide 26, why is the MC at 14 lower than the MC at 5 inches? Oh, inch, sorry. Why is the MC at 14 inches lower than the MC at 5 inches?
So slide number 26. Ooh.
Yeah, 26.
There
we go.
And why is it? Yes, Raul, you wanna?
Yeah, I mean, this is something that we're still working on. We research, mineral research, and the Office of Materials and Road Research are working quite a bit on that complex moisture distribution, and I want to show you some plots from some work done by UAP, Dr. Teixeira Segeye, on that question. Due to the fact that we have, precipitation plus a shallow water table. Here I'm showing just temperature distribution. Here I'm going to show moisture. How moisture changes along a typical cross section in mean road with the seasons. So we have a very complex boundary condition because we have the water table very shallow, about 5 feet. It varies between 3 to 5 feet depending upon where in mean road you're located. Because we have, some of the subgrade. We have some subgrade that is sand, clay, that can hold way more water and can raise up the water table. So, and then that coupled with the precipitation, it gave us a kind of difficult distribution on profiles that are usually not homogeneous. Is not what we expect usually when we are analyzing the data. So we're working on it. We're starting to install more monitoring wells, groundwater monitoring wells, and trying to understand based on performance data and measurement of the soil water characteristic curve of these materials, why we have this flow and regime, this change, this unsaturated behavior. So it is a very good question, and we are working on it. We don't have right now a clear answer. We're gathering all the information. We just acknowledge how difficult it is due to, again, this environmental condition and this the shallow groundwater table location at Mead Road.
Next question is, do you think the performance of RCA changes if 186 and 187 has clay loam as subgrade? How do you think it will compare with 188 and 189?
Raul, if you don't mind, go to box plots.
This one or the one from?
Yeah, this one. No, this one is fine too. Yes, we show it composite here. Of course, having a sand subgrade will have slightly impact, but we also did the baked layered analysis. So we did predicted the elastic modulus of each layer separately, and that ends up giving the same trend. Again, yes, composite elastic modulus may change, but layer-based elastic modulus were the same. Coarse RCA and fine RCA perform better than the RCA wrap mixtures, and RCA wrap mixture perform better than the limestone.
All right, next question is, what version of ME was used in the study? National calibrated values?
It was the one before the last updated one. Those numbers changing a lot. I don't remember the last, but it is the one right before the one that came out last time. So it is version 6, or I don't remember the exact version, but it is the previous most updated one. Yes, we use the national calibrated values. The pavement ME study really just to do a preliminary, I mean, extensive but preliminary check to see how thickness values may, the base layer thickness values may change.
All right.
Well, but we have very good questions.
Yeah.
we do have quite a number of questions left, so I will try to keep it short. Otherwise, I will connect the askers to the answerers. What happens if the layer below is chemically treated subgrade? Do you recommend not to have chemically treated subgrade below RCA?
I'm not sure if it is environmental concern related question, but it would it would always to have much stronger sub base and subgrade, and I would, if there is a budget, I would recommend the agencies or contractors to use, if it is needed, of course, the cement treated subgrade. I don't see any problem with that. What do you think, Raul? What's your take on that?
Yeah, I think so. I don't envision any potential issue.
Yeah. And I think, yeah, go ahead, Lauren, the next question, I guess.
Okay, we'll make this our last one. What metals are typically to be expected from a RAB layer?
Yeah, it is very variable. I think chromium and iron that we extensively studied, but they are not in high concentrations. Zinc is another thing, and this happens because of the presence of sometimes reinforced steels. Where you get the concrete is very important. The source of the concrete, is it from the aged pavement performance, or it is demolu, like some concrete layer that is like demolished large structure or bridge pile. Depending on that, the sources of the metals the type of metals may change, but overall iron, chromium, and zinc that we extensively studied.
Lauren, I just want to add a comment. I think Yoav's comment is quite important before we close. So he's stating that You're finding, Bora, regarding RCA's higher water absorption capabilities and higher stiffness than other base aggregates appear to justify some of the tenting issues observed in winter in cold region roads. Last year, his group tested over 100 miles of roads suspected of tenting, transverse crack heaving, and the severely affected sections had one thing in common. They used the recycled concrete pavement as base aggregate. So his comment and suggestion is that the design of RCA in cold regions should take into account tenting. So I think that's a very good observation to include in some recommendations. Although it was not part of the scope of this work, I think that that's something important to highlight.
And Lauren, one more thing. I think Chris Brackey have a very valid question about identifying tufa formation in the wrap layer.
Okay.
That we didn't study particularly. That's why we wanted to do the future studies. Raul mentioned we want to do forensic analysis on the in situ test sections to get a core, and that's the time that we will look into the tufa formation. That's a very good question, and that's the time that we really with that future study forensic analysis, we get a core of materials and look into that calcite formation, if did it really happen or not, to observe it.
Okay. Well, we are just past the hour now, so I think we need to wrap it up. But thank you so much. This was a very engaging presentation today. This has been recorded and will be available on our YouTube site by the end of the week. Please join us next month on May 18th as we discuss some seismic intelligent construction technologies project with Jason Richter and Chun Park. And we hope to see you then. Have a great rest of your Tuesday and stay safe.
Thank you.
Thank you, Bora.
Thank you.
Thank you, Lauren.
Thank you all. Thank you all.
Thank
Thank
you.
you, Lauren.
Bye.
Thank you, Raul.